Okay, great. Well, good afternoon, everyone, and thanks for attending today's session. This is the part 2 of the IRC. So this webinar will be recorded, and the recording is usually posted to the Code Adoption Toolkit within like a week or so. So keep an eye out for that. But if there are any issues with audio, feel free to write me in the chat. My name is Erica DeLello, and I'm a project manager for Noresco. This series is sponsored by the Colorado Energy Office with training materials created by Glenn Mathewson. So thanks, Glenn, for creating the content today.
Yes.
So Glenn and I have been working with the Colorado Energy Office to put on a whole bunch of trainings. This is just one of the webinar series. We'll be adding to this series as well, because currently we only have through the 14th. So we'll be adding a whole bunch more trainings. So definitely keep an eye out in your email to register for any other trainings that we add to this series too. And then we do offer tailored group trainings, or like if you just have a group of 10 people that's interested in hearing more about the energy code, we can come and train you guys on it and continue to provide those continuing education credits as well. All right, so with the Code Adoption Toolkit, most of you know about it by now if you've been attending these webinars, but that helpline is still available to you guys, and we are on it answering questions on any of the I codes and roof structure codes within the state of Colorado. So if you submit a question, a subject matter expert will get back to you in just a couple days' time. But definitely utilize that. And then today, throughout the presentation, we want to encourage those questions. So go ahead and use the Q&A function or raise your hand. And lastly, there will be a survey window that pops up throughout the webinar, pops out at the end of the webinar. If you could take a minute to provide feedback, well, we can use that to continue to inform which webinars we train on and to improve. So with that, today's presenter is Glenn Mathewson, and I'll let him take it from here, introduce himself, and dive into the content.
Great. Thank you, Erica. Let me get my screen share working. Okay. And hold on, let me just do a little housekeeping now that I have control. Open up that chat box. There it is. Okay. All right. So this is kind of a continuation of what I started January 3rd, I believe it was, a Wednesday. And it was a brand new presentation I put together. I'm kind of an IRC guy. I mean, I'm a code consultant and educator, and I've got my certifications and all that. But my passion really lives in single family homes and duplexes and townhouses, all of the structures that are going to be regulated out of the International Residential Code. So I was really excited to be a part of this team offering this training. And I went right into creating a new webinar for January 3rd, all about IRC Chapter 11. So many folks talk about the energy code, the energy code, the energy code. But when it comes to home builders and people that are working in the residential industry, we'd like them to have the code book for the residential industry, which is the IRC. And so to continue to message to that industry specific area of construction professionals and code professionals, and to message to them this other book you've got to get, well, that just instantly makes things already more cumbersome, right? More difficult to dive into. So I was real excited to put together a presentation about Chapter 11, which is the IEC provisions for the buildings regulated under the IRC, all pulled into Chapter 11. Well, of course, like I tend to do or anyone does when they're passionate about something, sometimes they overdo it, right? So I prepared way too many slides for what I could get through in that first 1 hour. So that's what we're going to pick up on today, is continue with this webinar, but now we could sort of call it this webinar, right? Because now this is really what I went after. This is kind of where I left off, or this is exactly where I left off in the first presentation. And so we could call this 1 hour webinar now sort of the compliance pathway webinar. I'll do a quick introduction for myself. For those of you that have not met me before or gone through an introduction, this is just a kind of collage of my last 2.5 decades of my career in construction. I started at age 19 as a laborer, and I've worked my way up from being a laborer to independent code consultant and educator. I spent a lot of time framing homes. I had a deck design and construction company. I started working for City of Westminster, Colorado in 2005, and then left there in 2018 to go independent. I write for Fine Home Building Magazine, a regular column called Know the Code. I attend the code hearings and have for the last 10 years. I encourage anyone involved in the construction industry to participate in the future of the construction industry, which includes codes, and collaborate and contribute your experiences and opinions in that code development process. Whether you're a building authority hearing this or whether you're a tradesperson hearing this, it's the same message I send out to both of you. And so I walk the walk, or I walk my talk, and you can see here where I've aged through the years from when I first got involved in code development. I write ICC's book on deck construction. I have an online website, buildingcodecollege.com, etc. If you want to learn more about me and links to my social media, my YouTube, and things like that, you can go to glennmathewson.com. All right. Now, Erica already told you about this, but I'm going to tell you about it again. This is the Colorado Codes Helpline, and I'm telling everybody about it. Why? Because I think it's super cool. And guess what? I'm involved with it. I'm one of these subject matter experts that get to receive these questions and dig in and find out the amendments and look up the information and give you my professional interpretation, which of course is just help. It's just assistance. You will still need to work with your local building official, or if you're the local building official, you of course have that authority of interpretation to make your decisions. But I love to share this because I'm so happy to be a part of it. All right, quick little reminder. I already said I did a 1 hour. I sort of did the first hour of this webinar, and I'm just showing you here the Colorado Energy Office's YouTube page. And you can see right there, it looks like it's one of the more recent ones uploaded. There's my presentation that occurred just prior to this one. Now, I don't think there's anything I'm going to present today that is going to be confusing if you didn't see that first part. Maybe I'm wrong, but I don't think so. But anyway, just pointing you out to sort of the first half if you didn't see that part. After this, you could always follow up with that at their YouTube channel. All right. So this is one slide that I went over in the previous webinar, and I just wanted to pull it up again because I'm going to double down at the end on something that I talk about here. And like in that first one, I made a big point to say that the energy code is not about reducing energy use. I mean, that's the way it's framed to all of us. And yes, that's kind of the goal. But remember, nothing stops you from building a 1,000,000 square foot house with 17,000 heated pools. That's ridiculous, but that's the point. If we were going to reduce energy, we would put limits on what you can actually use. But we're not doing that, and I'm not sure we ever will. What we are requiring in the energy code is effective use of energy and conservation of that energy as you're using it, to not be wasteful, right? And so I just want to double down on that it's really just about being mindful with our energy use, for a paraphrased term. All right. So where I had ended off last time was I was working through my goal with that first webinar, that definitely is not for 1 hour, was taking you through all these sections of chapter 11. And I went through section 1, 2, 3, and 4, brief, different levels of depth in all of those. And then I came to sections 5 and 6. And this is where we get into what I call the alternative pathways for compliance. And this is the part that was to open up this whole discussion now about compliance pathways. And so that's where this webinar is going to begin. So, of course, we're in Colorado, right? And I don't know about you, but I'm a snowboarder, actually a snow skater. Maybe you're a skier. Maybe you ride a snow bike. I'm a believer that for sports people to enjoy the mountain in the way they love to enjoy the mountains. And guess what else we get to do? We get to take all kinds of different paths. But we all start at the top of the lift and we all end up at the bottom of the lift. But we've got different devices and different ways that we go there. I've got a family of 5, and I can tell you we've got different devices and different paths to the end. And so I'm going to use this as an analogy because that's what I like, right? So here we are. We're all, my family of 5, we're all up here at the top of this hill, and we need to get right down here to the bottom. I mean, that's gravity's going to help us, and that's code compliance. And so this is what I'm going to do is give you like a 30,000 foot view, kind of like we have right here, of these compliance pathways. All right, so let's dig into this. Have a drink of water. Always drink your water. Okay, so our prescriptive pathway is the first pathway that I'm going to present to you. And it's the first pathway presented to us in chapter 11. And so of the prescriptive pathway, there's actually a few different paths under prescriptive. The first one might be this route. Maybe we're going to go down this mogully run here. I don't like moguls myself, but maybe you do. So you'll pick this route, the U factor route. Now, what prescriptive is in general, the way I like to present it and get our brains wrapped around this, I'm a big analogy kind of guy, trying to take code that's complicated and bring it down into something that's more familiar to everybody. So what's familiar? Well, probably that Better Homes and Gardens cookbook on the left right there. I mean, I'm guessing most households across the US have that one, maybe the older households, but they've been on many, many new editions of that. And this is a recipe book which gives us recipes and ingredients and procedures of how to make a safe meal for your family, or if you've got more guests coming, etc. And so that's really what the IRC is it's just a cookbook, and it's going to provide some very basic recipes for how to build a safe home for your family. But of course, like this Better Homes and Gardens cookbook, it's going to be limited to the recipes that are provided in it. And who promoted and suggested that those recipes get included. In the same way that new editions of the Better Homes and Garden cookbook are going to include newer and more modern recipes, and maybe get rid of old recipes that aren't as desired by the society anymore. The same thing we see happen with the IRC every 3 years, and that's in that code development process. All right, so we're going to look at a recipe. And of course, there's so much more to this. This is a 30,000 foot view. But the recipe basically saying, all right, we want to conserve energy inside of this house. How are we going to do that? Well, let's start by looking at the common ingredients of a house, if you will, right? The common dishes for a nice meal, an appetizer and a main course. And so here at the top of this heading, we can see we've got fenestrations and skylights, like doors and windows, skylights. We've got glazed fenestrations. There's our windows. And then you've got the solar heat gain coefficient for them. This is about the heat coming into the window versus the heat from solar radiation coming in, etc. We've got all these different assemblies here, our ceiling assemblies, our frame wall assemblies. And notice here it says frame wall. It doesn't say wood frame or steel frame, because this is going to let you drill down to figure out exactly how you're going to build that wall. And you analyze every little piece of ingredients in that wall. And so as you can see the rest of the way down this side here, you've got floors and basement walls, all these different parts of the thermal envelope that interact with heat movement in a different way and with different common construction methods. And so the code recipes are designed around these typical common methods and common materials that are used. So if we look at this example, and we're in Colorado, we've got climate zones from 4 all the way to 8 in our wonderfully diverse state here. However, when it comes to this new 2021 IRC, the majority of the provisions for conserving energy, you've got a lot of similarity now in all of the climate zones that are in Colorado, that happen to be in Colorado. So as we can see here, we've got a maximum U factor, and U factor is a measurement of heat movement through an assembly, whereas R value is a measurement of resisting heat movement through an assembly. And both of those are heat movement over time, right? Even if you have a Yeti cooler, the best, most expensive, fanciest cooler out there and available, I don't know, maybe there's a better one. Sooner or later, if you don't add more heat to it or more cool, sooner or later, the temperature inside the cooler will be the same as the temperature outside the cooler. So it's about how much we block or allow movement of heat per time, because sooner or later, it's all going to escape or get in. All right, so if we looked at this from an R value standpoint, we would take the reciprocal of the U factor in order to calculate and get in our minds what an R value is. So if we look at a U factor of 0.045 maximum for this frame wall assembly, divide that under 1, and you can see it's an R22. But that is an R22 essentially for the entire assembly, not just for the insulation that's been put inside of it. With the U factor method, you calculate out and you get to determine the performance of your assembly by specifically what you built. So it's going to count for the studs in here. Studs, right? They have a pretty high U factor. They're going to allow movement of heat energy faster through the studs than, say, through insulation. So whether those are metal studs or wood studs, it's going to have a different U factor. This recipe lets you get credit, or you count you for exactly what you're using. Metal studs or wood studs, 24-inch on center, 12-inch on center. How is your assembly built? We're going to count the U factor of every piece. So we're going to look at the drywall. Hey, if you had no drywall inside your house, the heat's probably going to move really fast to the inside of the stud cavity, right? But if you had drywall there, well, the heat's going to move a little bit slower. So there's a U factor to the drywall. There's a U factor to the sheathing on the outside. Now, of course, you're probably going to have some cavity insulation. There's a U factor to that. But you wouldn't be able to calculate that for the entire area of wall because the cavity insulation is not taking up the whole wall, right? So if it's studs, wood studs, 16-inch on center or 24, you're going to include that in these calculations. And then you even can get credit for air film. Just the way the air interacts with the surface material actually creates a tiny little bit of resistance, or a calculative method of that heat moving through there. And then, of course, you could add to this continuous exterior insulation, and then that would be another part of this assembly. So basically what this is like a build your own pizza. It's kind of like saying, hey, I need a pizza and I need 1,000 calories, or I need 10,000 calories in this pizza. So you are going to count up the calories of everything, right? The cheese and the bread and the toppings as well, all of it, to figure out the calories for the pizza. And I'll bring that analogy back here in just a little bit. So this is a very high level way of looking at what the U factor method is. It's saying, hey, we've got this table. It's got the conventional ways of building: framed wall, basement walls, wood, framed walls, conventional, normal stuff, right? Better Homes and Gardens cookbook. And it's just saying, design it however you'd want, but don't allow the heat to move through it any faster than this maximum U factor. Okay. But there's another route. Maybe you're going to offshoot. Maybe you come down this route partially on this path, and then you shoot off for a little side shot, and then whoop, you reconnect right at the end again. And this brings us into another prescriptive path, or you could call it an option or a modification of the original path. But I like to look at it as really a different path, because it is a different approach to designing your overall building. And so in this path for total UA, we're going to go back to this same table. And we see all these different parts of the meal, so to speak, right? Appetizers and main dish and dessert, and all put together, we see the amount of calories, let's say, that we're going to have in this whole meal. So same way we're building a house, it's going to have floors and ceilings and walls and windows and all these different assemblies that are identified right here in this recipe. Well, let's look at, for an example, at this climate zone 5 and marine 4 and come across here. And if we look at the fenestration U factor for a window, we're going to see it's a maximum 0.3 U factor. So we can't be higher than that number. And then we see for the framed wall U factor, it's 0.045. That's a much, much lower number, right? When we took the reciprocal of that, it was like R22. If we take the reciprocal of 0.3 U factor for that window, that's like an R3, right? Just a little over an R3. So we understand in construction, our windows do not have the same resistance to heat movement, or in U factor terms, they allow heat movement through much more rapidly than our other insulated assemblies. So, but let's say you've got a different plan. Let's say you got maybe you're designing a house with a little reading nook on the second floor. I've seen this. A friend of mine's got one of these in his house. Little tiny, little small reading nook up there, but it's already kind of a small space, and you're really trying to maximize the square footage of that space. So maybe you want to try to build a smaller wall assembly in that area so that you can get more square footage and less thickness of wall. That'll be less insulation in that wall. So maybe you say, hey, I'm going to buy a really high performing window. Now, this is a manufacturer you see here, but just FYI, if you see any manufacturers in any of my education, I just picked it as an example. I do not do any product endorsements. Please buy whatever products you feel are best for you as a consumer. But this is a great example. It is a Colorado company, so I always give a nod to Colorado. But take a look at this window I found. They have a window upwards of an R11, not an R3 like the reciprocal of 0.30, R11. So that's a high performance, like a triple pane window and probably all kinds of other technology. I'm sure you pay for it. 0.09 U factor. So that's a much better window. So let's say we got this recipe and we need a certain number of calories to successfully, throw this party, right? We need a certain amount of resistance to heat movement or a maximum amount of heat movement through this. But we're going to buy in our reading nook, we're going to buy we want to buy a really good window there for whatever reason. Maybe again, to maximize square footage. So one of our windows, we're going to go with a better window. Instead of the minimum code, we're going to design it with a 0.09 U factor, a really good window. Well, now we're above code in our thermal envelope, right? But that wasn't the goal of that choice. So what this allows us to do is say, all right, I've enhanced the resistance to heat movement, or I've limited the allowance of heat movement in this one part of this meal, right? This one part of this house, the better window. And since I've made that part better, I can make another part slightly worse, right? I hate to say slightly worse because in the end, right, you're still going to have a meal with all the necessary calories for all the people coming to your party. You're still going to have a house that meets minimum code in terms of energy conservation and effective use of energy. And so this might allow you to take that reading nook and say, oh, let's drop that down to a 2x4 wall, minimal insulation, but we'll offset it by putting a better window in that location, and we maximize the square footage that the homeowner desired. Totally random example, but it's exactly what it is. It's an example. With this understanding, how can our free American public go out there and design homes that are still going to do what the code wants, but give them more flexibility? That's what this method offers. And then, of course, this is just an example of window trade-off to wall assembly. All of these various things can be traded off. And again, this is a 30,000-foot view, so there are, of course, some additional nuances to all of this. But what I like to bring up, and this is something from the first presentation, I talked a bit about history, is probably why I got delayed and wasn't able to get through all the material. I gave a little discussion about the history of energy codes and how we got to where we are. And so I like to bring this one up, that this method, this total UA method, is one of the original ones from the late 70s, early 80s. You can see here from the Model Energy Code in 1983, one of the performance approach compliance methods, the U value of any assembly may be increased, and the U value for another component decreased. So this is not new. This method's been around a while, and probably because it's effective and it works to comply with code, but still give the free public as much design freedom and control that we can offer. Always trying to offer more. Now, this can be pretty complicated, right? You've got to figure out the areas of these assemblies and the U factor of these assemblies, and you're starting to get into a fair bit of math, right? You're getting into having to crunch some numbers and work some papers. And so luckily, part of just all of this support to energy codes, the origin of all this comes from our federal government back in the 70s. There's some fun stories there. So, if the federal government's the one that really got energy, the talk about energy, conserving energy in buildings going, they're still the ones continuing to help fund it and make it possible for trainings like this. Well, they better help out, right? And so they have. And the federal government, the energy office has been helping out for a long, long time with the free use and free ability to use this software called ResCheck. And I'm sure many of you have heard about this. You can get an entire 8-hour long training, I'm sure, out there somewhere on ResCheck. So that's the end of what I'm going to talk about this today. But this is a program that helps that heavy lifting of doing all the calculations of your assembly areas, the U factors, and helping you be able to trade those things off using something that we all find helpful in many things, right? Computers. All right, but there's another one. There's another prescriptive path. And, if I was teaching this class under the 15 or even the 18 code or any older code, I actually would have started out with this path. But I can say one thing that has shifted a little bit in the most modern edition of the Energy Code, of the IRC, the 2021, is this path is no longer presented basically as the first path. Now, kind of the first out the door path presented to you is the U factor path. But nonetheless, this path is probably familiar to many of you. It really is the simplest one in terms of thought process, in terms of design for compliance, and it's the R value path. The R value path is the most cookbook simplified, one size fits all pathway there is. It is full of assumptions about the envelope, because in the R value path, you don't analyze the R value or the U factor of any piece or part of that assembly except for the actual insulation materials in that assembly. So not the drywall, not the studs, not the air film, continuous insulation, cavity insulation. And so that makes it very simplified for design and for analyzing it. But it also means it's like the build your own pizza, right? With the U factor method, if I need a 10,000 calorie pizza for this party, I'm going to count every piece of food in that to get to that 10,000 calorie. Takes a little bit more work. You're calculating, the salt in there. I don't know, the bread, the tomato sauce. The R value method says the same thing. You need 10,000 calories to feed everyone at this party, but we're only going to count the calories of the toppings. That's it. We assume you're going to have bread. We assume you're going to have sauce. We assume a certain amount of cheese. We embed the assumptions of those values, assuming, again, some common assemblies. And then we're just going to go, all right, you got bacon and sausage on here. Boom, let's count those calories and we're done. So very simple, but ultimately, right, you're producing something similar but slightly different. All right, so there's kind of a rundown on that, and this is going to take you to a different table for the R value method. Now, if you look at the top of this table, it looks a lot like the table I just showed you for maximum U factor. And this table still has maximum U factor for the windows, for the fenestrations. Fenestrations we don't really ever look at in an R value standpoint. So we still see U factors for those. But notice everything else here changed to R value. And let's look at that same column for our walls. But the first thing I want to show you that is a subtle change, but it drives home, it supports the point I'm making to you. Notice what this column says. Wood frame wall R value. So in the U factor table, it was just frame wall, steel or wood. You're going to calculate it. For this table, it's assuming right? It's already just saying, no, you're building out of wood. We're making it really simple. Most people build out of wood. So there, right? Most people use regular bread in their pizza. So it's just going to assume bread. Okay. If you want to use a gluten-free cauliflower bread or steel studs, this is going to take you to there's going to be a different table for the R value. And I don't get into that one in this class because why? Because steel framing is not very common, right? So even the code, these recipes, they're based off of what's common, what's in everybody's pantries. So wood frame wall. Anyway, what we can look at now, if let's go to climate zone 5, and what do we see? We see some different values. First of all, we don't see U factors. We see cavity, or we see insulation R values only. And there's a lot of choices in there. Or look at all the ors, or. Now, this is one I like to bring up for any members of the public that are on the line. I hear often when I'm teaching the public, man, I would learn the code more and embrace the code more if it wasn't like it's written by attorneys. Man, they make it so hard to read. And I like to flip that on the public and say, typically, most of your complaints about how complicated the code is to give you as much freedom of choice as possible and to draw the line of minimum code compliance as absolutely specific as possible. We generally don't draw that line of minimum code with a 4-inch wide brush. We're using like an artist's little fine horsehair brush. And if you're going to draw something much more detailed, it's obviously going to be a little more complicated, right? And so that's something I know it's probably a majority of regulators on the line and attending these webinars. But anytime I offer something to you about the way I teach the public, don't be bored by that. Take it as a train the trainer moment. Speak to the public this way. Help flip their negative attitudes into positive attitudes because usually it's just a lack of knowledge and education that's the gap between the two. Anyway, that was a little tangent. Let's take a look at these little ors we got in here, all these choices and options. First one is cavity only. Woohoo! R30. Yes, that's shocking to a lot of people right now because that's definitely increased from previous codes. So R30, what would we need to do for a wood frame wall, basic recipe kind of construction? Well, you're looking at building with something like a 2x10 stud wall. So that's a choice you may want to make or you may not want to make. You know, I don't question why people want to take certain runs down the mountain. It's what they prefer. Same thing for our free designers out there. And what about this one, the other option? Now, this is doing R20 insulation in the cavity and then R5 insulation, continuous insulation. And that's generally on the outside. Granted, there's nothing specific in this as to which side of the assembly that would be on. Remember, insulation has a lot to do with vapor management and condensation. So you have to think about all of your thermal choices in design and how they are going to affect your vapor management choices. But that's outside of this class. And that's one of the reasons typically we see insulation put on the outside when people are doing continuous insulation. But what is R20? Why did we pick R20? Why is the recipe use that? Well, because that's common ingredients available on the market. That's what common insulation manufacturers produce. Why, Glenn? Why do they produce R20? Well, because it fits in the common studs that are out there in the market. So much of code is developed around what we already have, around, I hate to say baggage, but things that we really don't have a lot we can do with. Yes, 2x6 studs are always going to be around. So manufacturers of insulation make insulation to fit a 2x6 stud. And so the code says, hey, if we're going to write a recipe, let's use ingredients that are in everybody's pantry or at your local grocery store, right? So what might R13 and R10 be framed around? You already know the 2x4 stud wall. Choices, choices, choices. Hey, maybe you've got some really interesting ideas where you want to do open cavities inside your walls. You like that rustic look, you know? Hey, maybe you like moguls. I think you're weird. You might think I'm weird. That's the beauty of this code and my analogy to skiing. If you're getting bored of it already, tough. So what do we have? We have an option of continuous only on the outside. So now you could put no cavity insulation with a cool rustic look of your walls if you'd like, or go ahead and put drywall on the inside, but you don't have to worry about anything in the cavity. And this is just an option to allow you to use any kind of stud wall that you want and put all your insulation on the outside. So complicated, yes. More words in the book, yes. But when you understand them, what does it mean? It means more freedom of choice and flexibility in design to the American public. Who can complain about that? All right. So what else do we have as part of this building thermal envelope? We want the heat in or we want the heat out, one or the other. And this is Colorado, so we're generally trying to keep the heat in, right? And so what else might be a part of moving heat? Not just through solid materials via conduction, but heat also moves via convection, air movement. And so any air infiltration and exfiltration of our thermal envelope is bringing heat in and out. And so we have a definition for air barrier, and we get a whole section in the building thermal envelope about air barriers. Now, in the same way that a hot air balloon rises, it's not really the heat rising, it changes the air pressure. And so it's technically it's air pressure difference that makes the hot air balloon rise. But let's keep this simple. We're 30,000 foot view. We're in this hot air balloon looking down, right? So in simple terms, warm air inside the house is rising. And when it rises, it's going to be escaping, and it's escaping generally out of our ceiling assemblies. Well, if air is going to be escaping one way, it generally means, oops, air is going to be being pulled in from another way. And again, this is just an anecdotal photo, but this point still drives home that if you need to retrofit an existing home, like my 1958 house, last summer, I did some work in my attic, and that's where I did the air sealing. Air sealing in your attic space to stop that warm air from rising, you're basically attacking the very first issue. If the air is leaving, it's going to be drawing more air in, whether we could have no wind. So this is why we see often the first advice for air sealing on older homes is to get up there and air seal your attic. Stop the air moving out so it stops the negative pressure wanting to draw air in from below. But then, of course, sealing other locations great for issues like wind pressure. That's a different pressure now that may be moving our air in and out. So anyway, we test this and we say, all right, now in the modern code, you're going to be doing your blower door test, and you've got to prove that you are not going to be more leaky than 3 to 5 air changes per hour. And the 3 to 5 is due to the different climate zones. Going off memory, climate zone 5 is when we get 3 air changes per hour, but climate zone 4 in Colorado, you guys are on the 5 air changes. So this is why we see this little range there. All right, so there's our 30,000 foot view for our prescriptive pathway. Now there's so much more to this prescriptive path, and to be honest, this is the one I'm very passionate about. I live in a rectangle house, a 1950s rectangle. I have a dream still to build my own house one day, and you know what it's going to be? It's going to be a rectangle with a really simple roof. That's me. That's my style. And so I love the prescriptive method. Keep it simple. Give me a recipe and let me just use basic assemblies and build a basic house. So because I have a passion for that, that's what us teachers, all humans do that, right? We generally move in the direction of our passions. So since this is one of my passions, this will probably be one of the next webinars I put together because I'm already biting my tongue. I want to tell you more about this pathway, but that's my plan. Hint, hint, putting together an hour that's going to be all about this prescriptive path. All right, let's keep moving because boy, I'm already setting myself behind time. An hour goes really quick. Let's move on and look at these now. So all of that prescriptive path, that's really all still up here in 1102 building thermal envelope. And I went over that section at a 30,000 foot view in the first webinar. But this is the section where the prescriptive pathways, those 3 pathways, lie. But now we can get further along in these sections and continue our path through this chapter with these 2 alternative pathways. And so just like with making a meal for your party, maybe you're going to use a cookbook and just do a basic thing and follow a recipe. But maybe you got some other crazy ideas in mind that are a little outside of your wheelhouse. And so you're going to bring in what? A chef, right? A third party additional professional to help you create a wild and crazy dish for this party, like something no one's ever seen before. It's not in any recipe. That's my analogy of what you do when you go to the next two pathways. So let's think about the first pathways I talked about, prescriptive. All three of those prescriptive pathways, we measured conservation and use of energy with known physical properties of materials, right? U or R value and U factor, measurable values of materials. And then we also had the maximum air leakage, right? A measurable value, a quantitative value of air moving through an assembly. So this is one way to evaluate conservation of energy. What's another way we might be able to evaluate how much energy we're using? And that's going to be directly related to how much we're conserving. Well, in a live class, we can talk a little bit more, but I'm going to give you the answer that you're already probably all thinking. We all pay for energy, don't we? It's not free, not yet. You know, the conspiracy theorists say it's hidden somewhere, but that's just fun. Money, right? Obviously, we all understand that metric. And so that's what this next option allows, the performance pathway for compliance. This is not about using R value and those things as your metric for conserving energy. It's about using money. And so if we look at this, let's say we've got two identical houses in our design process here. We have a prescriptive house. And this prescriptive house, we're going to build just boom, 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 right out of the basic recipe. And there's going to be some associated annual energy cost to that, which will be different depending on the region you're in. And that's all part of this. You know, you don't get to take one state's energy costs and apply it to your state to game the system. It's where you're actually located and what your regional energy costs are. All right. This is the standard house, the prescriptive house, referred to as standard reference design. There's a certain amount of energy cost every year. So now design that same house with the same size of assemblies, the areas of the assemblies, right? It's the same house in terms of area of assembly, but you're going to build those assemblies different. You're going to build things totally different inside this house because you've got that third-party chef, right? You're outside of the cookbook, and the goal is make sure your energy costs are either equal or less in energy cost. And if they are, you comply. All right. Well, this is also one of those old original ones from the original energy code pathways. See, if the calculated annual energy consumption is not greater than a similar building, referred to as standard design in the model code now, we call it standard reference design. So again, nothing new. So you might look at this house on the left, the prescriptive house, and like, okay, we're going to insulate the envelope to the table, you know, R30 cavity. And then we're going to do a maximum air leakage. And we talked about that maximum air leakage, 3 air changes per hour in most of Colorado. Okay, that's the baseline. Now in our performance method, what we might be able to do, and this is typically what is done, is a different insulation envelope gets utilized. And by different, I generally am saying a lesser thermal envelope is typically what people use this method for. But they offset that by doing less air leakage. Not like it, almost like that UA trade-off method, but not really, but sort of allowing you to play around with the different ways that energy or that heat energy and energy is lost or conserved in a house. So if you have less air leakage, you're losing less heat through convection, through air movement. So therefore you can do less, you can afford to lose more heat, i.e. less insulation in your insulated assemblies. This is kind of the truth be told. This is where we see a big part of why this option is chosen, because air leakage can be tightened up with building practices, whereas more insulation is hard dollars. So you trade off dollars of product for more meticulous installation practices in a nutshell. But there's a few other things here, window orientation and window shading, right? So if you know your prescriptive home is assumed that all your windows are facing in the worst orientation possible, whereas for the performance house, you can adjust the orientation of that building so that we're utilizing sun energy for heating in the summertime, solar heat gain through the windows. But maybe you've got window shading, so we're blocking some of that summer heat, so we're offsetting our cooling. But notice these are all permanent parts of the building construction. And so, like I said, this is kind of what ends up happening is rather than the maximum air leakage being that, folks are like, hey, we can build with less now. We can build one air change. I build a really tight house, and now they can offset perhaps the amount of insulation in an assembly. So this is kind of how some details of the performance method, or not details, but a high view of it. Now, one way that folks might be like, well, hey, I know how to offset energy costs, Glenn. Man, solar PV, it's the new hottest thing. We're getting all the rebates. You know, if I get to make free energy from the sun, well, I'm not paying for it. And that's the cost of energy. Nope, nope. Good idea, but wrong pathway for that one. Okay, you're trying to ride the speed of a blue on a green. Slow down on the green. You know that anyway. This does not work for this pathway. But there's more. There's still another. I see other routes coming down this mountain here. So we're going to do one more pathway. This pathway is the ERI pathway. And, you know, for you non-boarders and snow skiers, you're probably getting sick of me. But honestly, I saw this news recently about Keystone opening a new lift, this Alpine Wonder, a brand new lift at Keystone, all brand new train, new pathways to go down. Now, I used to ride at Keystone when it was just me and my wife, but then those darn kids came along and that got expensive. So we went to another resort. So I haven't been to Keystone in ages. I haven't looked into that mountain in a long time. And lo and behold, if I go back and revisit Keystone, Keystone added a new pathway for me. You see what I'm doing here? New pathway 2015. Sometimes we got to keep cracking open that book. We got to keep going back to the mountain we've been to because our memories might be different or there might be new things, new places to explore. So, yes, this is a brand new pathway. This isn't one of those old ones like I've been showing you thus far from the 1970s. This one came into the code in 2015. So remember, revisit your old ski mountains once in a while. They could be totally different. And remember to crack open your new code books because maybe there's totally different, more options for people. I personally liked that little analogy, and I'm going to run with it. All right, so yes, ResNet and this whole ERI method came into the IRC and Energy Code in 2015, but it's been around before that. You can see ResNet was developed back in 1995. This is a separate organization that was trying to develop a national market for home energy rating systems so that you could promote energy efficient mortgages, right? We appraise homes and value homes in America in just the most shallow, absolute shallow ways. How bad does someone want it? Ooh, now it's worth more. But these folks were trying to give potential home buyers of new or used homes a way to actually evaluate the real value of what they're buying here, not just how bad everybody wants it because it's in the coolest neighborhood. And if we're comparing two homes, which home is actually going to give us better energy efficiency? So that's what they were doing, was creating an outside of the code method of grading a home for efficiency. And again, this could be new or used homes. So much more cool stuff here to explore, but we're at 30,000 feet on this class. So here's just a slide from, it looks like this is a 2013 image of theirs for the HERS index. You notice HERS has this registered trademark because HERS is a registered trademark of ResNet. So this is similar to the HERS, but because of trademarks, it's not called that in the code. It's the ERI method. But if you look here in this grading system, when this was established, the 100, a grade of 100 meant code compliant to the 2006 IECC. So a 100 was a code compliant house at the time to the 06. And a 0 score was a zero energy home, right? Like, so for a home buyer, hey, this house scored a 30. I'm going to probably spend less on my energy bill. Now, I like this slide that it's dated and that you can see that this method of grading hasn't changed significantly. But what's changed is the pass or fail criteria for code. So as you can see here, in the 2006, a score of 100 was code. But on this same grading scale, by the time you get to the 2012 code, no, you're going to have to be at like a 70 in order to get passing. And so this just shows a little example of the evolution of the energy code itself, moving continuously towards more conservation and effective use of energy. And so now, again, we see that this has been pulled in as like, hey, if people are going to do this as a wise consumer buying mechanism, well, why not just let that same mechanism be a code compliance mechanism? And so that's what we see happen in 2015. And then now under the modern 2021 code, you can see what the passing grades have gone to. Just a little over 50. So 2006, 100 was code compliant, and now we're looking at in the 50s for code compliant. So what does this method allow us to do? This method allows you to get in even deeper than the performance method, and you can start analyzing the energy use of appliances. So things like how efficient is your HVAC and water heating? How efficient are your major appliances like a refrigerator or oven and stove? And how efficient is your lighting? Letting you drill down more. It's going to get more complicated. You're going to need that third-party help, right? And now is when we get talking about on-site energy, because how else are you going to get to a zero energy home, sort of the goal, if you will, the cream of the crop of this method of grading a home? You know, you're not going to get to zero energy by setting your thermostat to 50 degrees. You're going to get there by producing your own energy at home. So let's think about this for a minute. This is a photo I use in a lot of my classes from many years ago. This is Ominous Forks, Colorado. It's a ghost town. You can see it's way up in elevation. This is an old house built there in the 1800s. Clearly no insulation in this. Clearly, I mean, obviously this house could be bleeding energy out everywhere. But I'm going to build this house just like this today, no insulation, and I'm going to put a 250 million kilowatt solar system on the side of that mountain. And I'm going to make so much energy that I'm actually selling it back to Denver for you city schmucks. Does that seem sensible? Do I still have to conserve energy? Why would I need to conserve energy if I'm making it all for free from the sun? Well, let's look at this photo. Do you think if those solar panels were installed in the 1800s when this house was built, that they would still be there and we'd be visiting the ghost system and that we'd still be able to get power from those solar panels? No, we wouldn't. And so that's the concern with this method. We don't replace walls very often in homes, but we do have a much lower lifespan for things like high efficiency furnaces, high efficiency appliances, solar systems, right? So we don't want to put all the eggs in the free energy and low energy use basket and build a crummy house. And then 100 years from now, someone like me is showing photos of it going, well, they let them build this trash because there used to be a solar system. So we get backstops, conservation backstops, right? I like the baseball field because it's like throw the most wild and crazy pitch you can come up with, but keep it in the game, right? You still got to be over the whatever. I don't play baseball. Where the batter is, the home plate. All right. So what are some of these backstops? We can hop in here and see on-site renewables. If we're using this ER method with on-site renewables, it's going to tell us, hey, that building thermal envelope, though, there's still a minimum it's got to be. You can't be, you've got to be either greater than or equal to the levels of efficiency in this table from the 2018 Energy Conservation Code. I told you there was a big jump from 18 to 21. So this says, all right, if you're going to use solar, you don't have to, you can reduce some of the insulation values in the 21 code, but you can't go lower than the 2018. So if you see here, just as an example, 2018 was R20 cavity or R13 2x4 wall with R5 continuous. That's your backstop 2018 code. Here would be the 2021, right? The R30. So you can get a little trade-off of your envelope by using the on-site renewables. But again, as I've already said, we still need a core house that's going to last. You know, these houses last much longer than these efficient technologies. And if you look over here for solar heat or for U factor, notice there's really no change. You don't get any credit for window 0.30, 0.30, other than climate zone 4. And then, so you can see here, 0.30, and you're still stuck at 0.30 for this one. And same with solar heat gain coefficient. The only difference you would see is a little backstop for your solar heat gain coefficient. And again, that's only in climate zone 4 down here. So for the rest of Colorado, doesn't matter about your on-site energy, it doesn't allow you to put in worse windows. Why might that be? Well, remember what I said? Thermal performance is directly related to vapor management. So if you start putting in crummy windows that allow heat to move right through, no problem, because you've offset it with something else, you're going to have condensation forming on the inside of those windows, like the old single pane windows. Who's got an old house? I've replaced my windows. So we see some thoughtfulness in, like, yes, we're talking about thermal energy and energy conservation, but we still have a duty to protect from condensation and moisture and vapor issues. And hey guys, 2018 IRC, for you members of the public, you probably don't have code books all behind you like I do, but check it out. Make sure you go to codes.iccsafe.org and look at that 2018 code. So it can be frustrating when you got this modern 2021 code and you're all excited. I bought the code. I'm gonna be a professional. And it tells you go look at an 18 code, right? It's not a money grab. You can go check it out for free right here. I always promote this site. So let's see what another backstop is. Maximum air leakage rate. Hey, I got 1,000 million bazillion solar panels. Who cares how leaky my house is? Well, we care because your solar's not going to last. And so what do we get? Under no compliance path can you be more than 5 air changes per hour. So you might be able to trade off a little of your air leakiness, but not all of it. Almost the opposite way that the performance path, where most people are going tighter with their air leakage, this one would actually let you get looser with your air leakage. And then real quick, I'm running out of time, so we're going to hit just, I'm almost making it there. I got 7 slides left. So close. Next stop here. I skipped tropical climate because this is a Colorado-based class. And yeah, we're not tropical. So the next section is additional efficiency packages. And so I lied to you, but I didn't lie. You guys saw the picture. If you were keeping up with my analogy, we made it here and I said code compliance is here, but where's the parking lot? You're not leaving the ski resort yet. Oops, lie. You haven't reached compliance yet. We got a little bit further to go. We still got to take this little path here to get to the parking lot. And so that's where we get this whole new section here on additional efficiency packages or options. Again, trying to move the ball forward continuously in more effective use and conservation of energy. So we can see you've got, whatever the other paths you pick, you still got a little more you got to do. And you can, again, pick more paths again. So one path would be your thermal envelope is 5% even more efficient. Another one would be adding in more efficient HVAC equipment, but not including it in your analysis. So it's just additional. Or look at this, water heating. Now I kind of got a bone to pick. It says reduced energy use. And I think I think words matter. We should fix that in the future codes. Because if we wanted to reduce energy use and water heating, we would limit how much water. Because remember, you can use all the hot water you want, right? So what we're really doing is we're more effectively using energy to heat water. And so then your fourth option here in the additional is duct insulation. And here they use the words correctly. More efficient duct insulation. Because remember, nothing is stopping you from wasting all the heat you want. It's trying to get us thoughtful buildings so we conserve and effectively use the heat. All right, I'm going to try to run a few more minutes before Erica shuts me off. And real quick, it's just a few quick stories and high-level view of these last few sections here. And this is where we see that ball moving with energy code, where we've solved a lot of, we've gotten mainstream construction methods, people talking about energy code and really boosting energy compliance and conservation in new construction. Well, hey, now that we got that, we see as the modern code progresses, hey, let's start dealing now more with additions and remodels and repairs and change of use. So quick little couple slides on this. This is a little personal story. This is my house. There's my little 1950s rectangle. It's not a rectangle anymore because about 10 years ago, I built a detached garage like this. Now, all right, I built a detached garage. Do I need to insulate it? Well, the first thing we got to look at here is, look, the building thermal envelope. Didn't say dwelling thermal envelope, building. So this applies to any building that you're providing heat to and using heat and using energy. So we see here that says you got some exceptions to this, like a low energy building based on wattage per square foot. But yeah, if you're going to be heating a space and using the energy there, then it's saying comply with the full requirements of the energy code. And I had more fun stories we could tell about this, but I'm running out of time and some of the complications with these systems. But I want to move on to, all right, I'm building this garage. Yes, I could build this envelope sufficient to give the thermal envelope I need, right? I can, in terms of heat movement through the envelope. That's possible. What about fenestrations? So here we get a subsection under fenestrations for sunrooms and heated garages. And what does it give us? Oops, I meant to have a little box there. 0.45. So it's giving us some unique, not that 0.30 U factor, but a 0.45. It's letting us have worse fenestrations in a heated garage. And then the next one that just dropped down was a special thing for heated garages under air leakage. And here it's saying you don't have to do the blower door test anymore like you would do for the rest of the dwelling. So let's think about this, right? Thermal envelope, nope, you still got to do it. Fenestration, we're going to let you be a little bit less good. And air leakage, we're not going to make you test it to the air changes per hour. And why? Because right there, a garage door. This is again where the code is responding to the common ingredients and materials and things that are in everyday construction. At this time in human development, garage doors are air leaky. Oh, we haven't pushed the envelope, we haven't pushed the society, the industry to like developing and designing more airtight garage doors. And then, of course, garage doors are not as thermally resistant as your other fenestrations. So it makes sense, right? The code makes sense why we would have this concession for the garages. Now, for the air leakage, it points us back to this table where in the past, older versions of the code, we didn't have to test for air leakage. You simply did a visual inspection for air leakage. But we moved the ball forward. And as code got modified and developed, now you have to test for air leakage. But now garages are where we used to be with houses ages ago. Oh, now we still want airtight heated garages, but we're not going to make you test it. You can go back to this table and just do a visual inspection. So there's still air sealing rules for a heated garage, visual observation and confirmation, but not a test. Now, when I built that garage detached, big part of it was to expand my little house into our attached garage. There's a picture of my youngster. He's like 17 now, but yeah, my kids got to always keep your kids involved with what you do. So my he's got his face mask on. Anyway, what have I got going here? Additions, alterations, repairs, existing building. Where unconditioned space is changed to conditioned space, it has to comply with section 11 and 11.10, section 10 of chapter 11. So here I had an unconditioned garage being changed into conditioned space now. And so I would go over to chapter 10, which is for additions. And then we got a subsection of that's going to say, hey, this isn't an addition, but we are changing space conditioning. And so what I've done here is I've altered an unconditioned space to a conditioned space, and I have to now bring it into full compliance with this chapter. So that would mean I would need to fur these walls in for thicker insulation or continuous or do something to meet those prescriptive values for these particular assemblies and the ceiling assembly. And of course, this opens up so much more discussion, but we're still at that 30,000 foot view. You can also look at this section, section 13 of chapter 11, and this is specifically about change of use. But if you notice this subsection at the bottom of unconditioned space, and it points us back to section 10. Now, quick note, guys, if you notice here, it says N1108, get your pencil out and change that in your code book, because that's errata. That's an error in the printing. That should be referencing you to section 1110 over here, and then you would find this subsection. And then the last thing to mention on this is, remember, a basement. Okay, if I expand into an existing garage, but that garage, it's all built, it's an attached garage, but it's not part of the conditioned space. So I have to bring that into compliance, the envelope, because now I'm making it conditioned space. So I'm increasing the usage of energy. What's about this basement though? Look, there's no insulation in the floor. So even though it's an unfinished basement, does not mean it's not conditioned. This is still a conditioned space. And so finishing this basement does not change from an unconditioned space to a conditioned space. And so it does not kick in the same requirements we saw for the garage, which I would have to fur out the walls or thicken the insulation. This basement is already insulated. It's already conditioned. So if we look at this alterations part, it simply says we can't be less conforming than the existing building. So by putting a finish material over this isn't changing the energy use or making it less conforming. But now we can always read code with bias, and this can get weird. Then this next part says, hold on, alterations to buildings have to comply with these subsections. Well, I'm still altering this from an unfinished space to a finished space. And so then you go to the subsection and it's like, hold on, building envelope assemblies that are part of the alteration shall comply. So one, if someone was bias leaning to say, no, I want to see these walls increase to current code levels, they could stop right there and say, yo, you are finishing that wall, which is the envelope, therefore it's part of the alteration, therefore you have to comply with the tables for new construction R value. But we don't want to read code with bias. We want to read it with an open mind. So we got to keep reading to the exceptions, because the exceptions then say, hold on, if I'm not increasing the energy use, then I've got these two exceptions. Existing wall cavities that are exposed can simply be filled with insulation. Well, these aren't exposed. I'm not ripping off that, and they're already filled with insulation. So what about the next statement? Construction where the wall cavity is not exposed. So just taking through a path, again, more I wanted to kind of talk about on this, but got to wrap it up. So I'm going to wrap it up with just what I'm a couple minutes late. Thank you guys so much for attending this. And I hope that you will come back when I do the prescriptive IRC webinar.
Perfect. Thanks so much, Glenn. I know we went a little over today, but we'll give you some grace there. Give you, your presentations are always so fun and lively. They make codes fun, which is a hard thing to do. So
Well, thanks.
Glenn and I will stay on the line for like a couple more minutes. If anyone has any questions, feel free to just raise your hand and we can take you off mute or write in the chat. But thank you all for coming and attending this webinar today. We've got another one, actually the last two over the next 2 weeks. So definitely attend those and then keep an eye out for that email with more webinars on the way.
All right. Thanks, everyone.